Well, in order to be a good cosmic messenger, that is, in order to be a particle that can give us information about its source, a particle must be able to do two things. It needs to make it into our telescopes so we can detect it, and then it also needs to point back at the source that produced it so we know what we're studying. And light usually does a really good job at this. It's out this flash of blue light, a cone tracing out the path that it takes. This phenomenon is called Cherenkov radiation, and it's the equivalent of a sonic boom. It's also exactly what our neutrino experiments are designed to detect. One such neutrino telescope is IceCube. Located at the South Pole, this telescope is comprised of photodetectors, basically cameras, that are lodged 2 kilometers deep in the Antarctic ice. And these detectors are designed to pick up the Cherenkov radiation from passing particles. So on September 22nd, 2017, the muon from our neutrino went streaming through IceCube, leaving a trail of Cherenkov radiation in its wake. And if you trace that path backwards, it points you right to the neutrino, which points you right back to the source that produced it. Now, this neutrino that we've been following has been called IC170922, because that's what happens when you trust the physicists with naming things. And in the days following its detection, telescopes from around the world pointed to the spot of the sky where that neutrino had come from. And what they found was a flaring blazar. And this was a historic moment. It marks the very first time that a high-energy astrophysical neutrino was linked to a specific source. But there's a caveat to all of this. That remains the only high-energy astrophysical neutrino to be linked with a specific source. That meaning we can't rule out the possibility that it was just a coincidence. Not yet. We just don't have enough data. And that is where IceCube Gentoo comes in. This upgraded neutrino telescope will be 10 times bigger than the original IceCube. And this image gives a sense of the scale. The red region is IceCube as it is today, and the surrounding blue is where IceCube Gentoo will be. Now this is a massive upgrade, and if we're going to upgrade the whole telescope, we might as well also improve on the parts that comprise it. One such part is called the Digital Optical Module, or the DOM. It's the photodetector currently used in IceCube. It's designed so that Cherenkov radiation can come through the glass up top. It's then converted into an electrical signal and processed by computers. Now this model has been very successful, but there are a couple of setbacks for design that make it slightly less efficient than it could be. And one of the major ones resides in the glass housing itself. Cherenkov light appears blue to our eyes, but it's actually brightest in the ultraviolet. And ultraviolet light has a hard time getting through that glass. It just gets absorbed. This means that when you sit in a sunny window, you aren't as likely to get sunburned, but it also means that this detector is not very good at detecting the most important part of Cherenkov radiation. One of the models that has been proposed to mitigate this issue is called the fiber optical module. It would utilize something called wavelength shifting optical fibers. Optical fibers are basically long, thin pieces of plastic that capture light coming in through any angle and feed it directly to either end. Wavelength shifting optical fibers do this, but as that light is traveling through the plastic, it gets absorbed and then re-emitted at longer wavelengths. So when that ultraviolet Cherenkov light enters a wavelength shifting fiber, by the time it gets to the end, it will be blue, which is a color that, in this case, is a lot easier for us to detect. So this model has been proposed, and it has a lot of promise, but the fibers themselves haven't been very well tested at the short wavelengths that we need them for. And that is where my part of the project officially comes in. For the first half of the summer, I was tasked with building a computer simulation of an experiment that we would ultimately perform in a real-life lab. And this is a screenshot of the graphical interface for Geant 4, a particle simulation software, just after I shot a photon at a simulated sample of wavelength shifting fiber. That jagged yellow path traces out the photon as it's transmitted towards the end of the fiber, where in a real-life lab, we'd smack a detector on in order to pick the photon up. Now, the goal of all this is to compare our simulated results with real-life laboratory data. And if the two match, then you can be confident that the properties of this simulated fiber match the real-life properties of our physical fibers. That information is what we can use to figure out whether these fibers are going to be useful for neutrino astrophysics. So for the second half of the summer, I was actually performing this experiment. I mostly worked in an optics lab testing the efficiency of samples of wavelength shifting fiber. But of course, in order to know how efficient it is, you can't just look at the light that it outputs. You also have to know how much light you're shooting at it in the first place. For that, we use this direct setup and basically measured the intensity of the light beam. We then pointed that same light beam at the center of a 10 centimeter long piece of wavelength shifting fiber and measured the brightness of the light coming out of either end. Using those two measurements, we can calculate the efficiency of this fiber at transmitting light. And here is what we find. The plot on the right shows the wavelength shifting capabilities of the fiber. That tall, narrow peak corresponds to the spectrum, or color, of our initial light beam, while the broader peak corresponds to the spectrum of the light after it had passed through the fiber. And as you can see, the initial spectrum falls right on the border between ultraviolet and visible light, whereas the spectrum of the light after it had passed through the fiber is very solidly blue, so the wavelength shifting capabilities are working. Meanwhile, the plot on the left shows the efficiency of the fiber at transmitting light. And we find that about 12% of light makes it to the left, and 12% makes it to the right, for a total of 24% efficiency. Now, believe it or not, this is actually a pretty promising number, especially given improvements to the design of the detector. Now, the caveat is that there are still tests to be done and improvements to be made to the lab setup. We have some systematic errors that we need to correct for, but with these experiments, we're well on our way to determining whether these little fibers are truly the future of neutrino astronomy. Thank you, and are there any questions?